I have no.
Professor Mukhi?
Yes. Shall I start it?
Yeah, sure.
Okay, good evening, everyone. It's a real pleasure to introduce my very valued colleague, Dr. G.V. Pavan Kumar, who's going to talk about CV Raman. Pavan is really well known in ICER. I don't need to say too much, but he's an expert on light matter interactions. He understands and uses the Raman effect frequently. And I just, and I've heard actually, I think I've heard Pavan talking about Raman once before. Actually, Pavan and I shared a science day in the early days of ICER.
You're right.
And I talked on something else, mathematical, and he talked about Raman. So I just want to leave the students who are here with one thought. When we hear about, because I often talk about the life of well-known scientists, and when we hear about that, I just would like to make a point to students that what is the purpose of a talk when we talk about the life of a scientist? Is it for you to sit and say, oh, CV Raman was so great, I'll never be like that? That's not the purpose. The purpose is for you to find, and also, is it a purpose to try and be like CV Raman? No. I mean, you can wear this fancy pagadi and you're not going to become a great scientist. Okay. So that's not the point either. The point is, what are the key episodes, where he did something, some action, some experiment, some thinking, maybe some, getting some lab organized, whatever he did in his life. What are the things, what are the kind of leadership roles he played, which you also could make a part of your life in the modern context? I think there should be an inspirational kind of feeling when you hear about a person, but don't take it literally. You will also hear many bad things about Raman and also about Einstein and anyone else. That's all right. The point is, what can you take from it? I think it would be nice if students focus. With that very short little speech of my own, I'd like to ask Pavan to start his presentation.
Thanks a lot, Sunil. As Sunil mentioned, we actually have had wonderful kind of events which we were both part of. One of it was this particular science day. I very well remember that particular interaction. And it's always nice to learn more about various different things from Sunil, and also thanks to Science Club for giving this opportunity to discuss something which is, as Sunil mentioned, a very interesting topic to ponder over. It's kind of a biographical history of CV Raman, but I would want to emphasize more from the context of ideas, which actually played a critical role in CV Raman's life. And how he came up with few ideas, how he implemented those ideas, and how he also interacted with people, which probably has very interesting lessons for us to learn from various different stuff what we have known about CV Raman himself. So I call my talk as a history of ideas because Raman, interestingly, not only worked about on molecular scattering of light, but Raman touched upon some very fascinating concepts in physics and science in general. And one of the aims of this talk is also to give you an overview of some of the topics which he did explore by himself and also with his students. This is something which is very, very important. So all of us are aware, very well aware of the fact that 28th February is celebrated as National Science Day in India. This is to commemorate the discovery of Raman effect. This is a general statement which is usually given. An important observation confirming Raman effect was done on 28th February 1928 by Raman and his students. Okay, this is something and sometimes not emphasized a lot. It was Raman and his students who played a very critical role in this particular discovery, and therefore part of the credit also goes to his team, who really played a very critical role, as I will probably emphasize going further. So Chandrasekhar Venkata Raman, which is the full name of CV Raman, as you probably would be very well aware, went on to win the Nobel Prize in Physics in 1930 for this particular discovery. And there are also very interesting connections to quantum mechanics and the questions what people were asking during that time and how Raman connected to those concepts. That is something I would like to also emphasize in this talk. Now, my sources for this talk, without which I would have not been able to actually really put together this talk, are three books. The first one is the pictorial biography of CV Raman. This is something I would strongly recommend anybody who is interested in knowing more about Raman and his scientific endeavors. The pictorial biography is not only about pictures, but also has some fantastic text and commentaries on his papers and his general research ideas and other aspects, which was essentially commissioned by Indian Academy of Sciences, and it is also freely available online. It's a large file. It will take some time to download, but it's worth if you are really interested in exploring more about Raman. There's also an authoritative biography written on CV Raman by G. Venkatraman, and the title is "The Journey into Light." And this actually gives you a very detailed description of Raman, his life and science, etc., etc. And the third one is more targeted towards younger audience, more so from slightly more popular level description of Raman and his effect, again written by G. Venkatraman, where he distills various different concepts and various different aspects of Raman in a very nice kind of fashion, so that undergraduates and even school children would be able to appreciate this. So these are the three sources which I have exclusively consulted, and wherever I've used the original text or original papers and other things, I've cited it. Original content in all these three sources. That is the important thing. Now, there are 5 time periods which can be connected to CV Raman. And what I'm going to do is I'm going to actually connect these 5 time periods to different concepts in physics, which CV Raman kind of explored. The first one, obviously, 1888 to 1907. In this particular time, childhood education and undergraduate research, it is the first time when he actually starts venturing into physics research, and optics is the beginning of his exploration, which you will see it turned out to be the topic which he continued to work until he died. The next period is 1907 to 1917, where he becomes an administrator in Indian financial service and keeps up his interest in physics by performing part-time research at Indian Association of Cultivation of Science. And here he starts off his research on very fascinating concepts of acoustics and some aspects of optics. The crucial period, 1917 to 1933, is the period of the greatest action, so to speak, where he becomes a Pollitt professor at Calcutta University and a full-time researcher at IACS. This is where he actually does a lot of work on light scattering. And importantly, that is a time when, quantum mechanics is really, emerging. And that's the time where Raman brilliantly connects some of the ideas from the laboratory to the ongoing discussion on quantum mechanics. And that's probably one of the reasons why he also ended up getting Nobel Prize, because the topic was so contemporary and it made a very deep connection to some of the stuff what was already discussed during that time period. The next part of the life, 1933 to 48, Raman was a professor at IISc, and there he worked extensively again on topics such as crystal optics, crystal dynamics, and also a lot of interesting questions related to mineral optics. Okay, that is something which he continued to keep interest very high. And 1948 to 70 is when he moved to Raman Research Institute, where he actually founded and built the institute and continued to do research for next 22 years of his life. And there he actually explored human vision. That is a topic which actually was something he was very interested in even at a very young age. Optics of minerals, diamonds, floral colors, etc., etc. Now, I'll just give you a very brief overview of his childhood education and undergraduate kind of education, but I'll talk a little bit more about his undergraduate research. Raman was born on the 7th November 1888, a village near Tiruchinappalli in southern part of India, which is now in Tamil Nadu. 1903, he joins Presidency College in Madras. He gets a BA degree, and he's already an outstanding student. His parents, R. Chandrasekhar Iyer and Parvati Ammal, are very supportive of him. His father actually is a school teacher and also has some kind of interest in physics. In fact, there's also a very beautiful interaction between Chandrasekhar Iyer and CV Raman regarding some physics topics, and he actually tells his father how to go about to teach that particular topic to his students. It's a very interesting letter. As early as 1906, Raman publishes his first research paper. I'm going to talk a little bit about that in the next few slides. He gets a MA in physics in 1907, and right after that, 6th May 1907, he marries Lokasundari Ammal as a teenager, by the way. He's already just a teenager, but as you know, the times were such that people used to get married very early then. And 1907, he joins the financial civil service. Now, interestingly, you may ask, why did not Raman pursue higher studies in physics or basic sciences? It happens so that his professors do suggest Raman to actually go abroad and pursue kind of higher education, including research. And Raman does apply, and it happens so that Raman fails the medical examination, which is necessary for people to actually go abroad. And therefore, he would not be able to make the trip. And the next best aspect is for him to join the administration in the British government of India. And financial civil service is one of the very lucrative kind of jobs for educated people then. And therefore, he very easily cracks the exam. And his first posting in 1907 is at Kolkata. Okay, so I'm going to go to the Kolkata phase a little later. But first, I want to talk a little bit about Raman's exploration of optics, especially when he was an undergraduate. So these are some of the pictures. This was Raman in 1906 as a college student. And this is Raman in 1907. He's already an assistant accountant general. Okay, this is Raman's photograph. And turban was something which stayed with him all throughout the life. There's also an interesting anecdote about Raman regarding turban. If somebody is interested, I can actually tell you about that.
Sir, can I ask? Can I
Yes.
ask a quick question?
Yeah.
So, like his degrees were BA and MA. Shouldn't there be BSc and MSc?
Yeah. During that period of time, it was so that the Bachelor of Arts and Master of Arts was the degree offered in Presidency College. Although the topics in which he actually pursued his work was not only in physics but also in English. For example, you will see some of his writing is really good, very polished and extremely good. And his education was not only in physics but also in English and some other languages, and also chemistry. He did a bit of chemistry too. It's very interesting since you asked, because BA and MA, although they call these kind of degrees, even when I was a student, which was not very far away compared to Raman, even my BSc degree had English, Sanskrit, and other languages as part of BSc. Okay, so if you do not pass these languages, you will not get the degree. By the way, that is still there. I don't know whether it's still there in some of the universities. In the university where I studied, I had to pass both English and Sanskrit as part of my my education and things like that. So yeah, so he had a BA and MA degree in these particular subjects. Raman was deeply influenced by some very classical thinkers in physics. All of us probably would have heard about Helmholtz. Helmholtz coil is somebody who you have heard, but Helmholtz is not just about only Helmholtz coil. Helmholtz was a giant in classical physics. He actually did some remarkable experiments. He was a German, and this is one of the very famous titles of Helmholtz, which was translated into English. And one of the aspects of von Helmholtz is that he gave popular lectures on various different scientific subjects, including sound, light, and other things. Young Raman got deeply influenced by topics related to these natural objects and the physical phenomena in natural objects, which is going to inspire him to do some very interesting work in the course of his time period. He was also deeply influenced by some of the work done by John Tyndall, who all of us would be aware of the Tyndall effect and the scattering of light also related to the Tyndall effect. Raman, as a student, also communicated with people. You can imagine he's just a teenager, but he also writes to Lord Rayleigh regarding some of the concepts related to the light scattering. As you probably would be aware of, Lord Rayleigh had done some very deep and very, very vast amount of research in classical physics. And Raman is always interested in some of the scattering aspects. He held Helmholtz and Rayleigh at very high esteem, and he was deeply influenced by some of the work what these gentlemen did during their peak time. Now, this is first paper of Raman published ever, and this is as early as 1906. Okay, so he's a young undergraduate, and Raman published his first research paper on a specific topic related to the asymmetric diffraction, where essentially the idea is that he was interested in looking at the diffraction of light, not from the conventional slit, where the light is incident on this conventional slit, and you look at the diffraction pattern, but he makes a very interesting observation and also relates to some basic geometrical optics theory, where if you now take the slit and subtend a very oblique angle with respect to the incident light, you end up getting a very asymmetric diffraction pattern. Okay. Now, you may think this is just a curiosity, but it happens to be a very important problem, because these kind of diffraction effects are extremely important when you scale this problem to X-rays and other kind of frequencies, because these inclinations and planes are very relevant in solid state physics. And some of the work what Raman did as a young teenager, as you can see, demonstrator in physics at the Presidency College, Madras. This is actually from that particular paper. It's a snapshot from that paper. And the Philosophical Magazine went on to publish this. This also probably was in consultation with some of the ideas which Rayleigh had already proposed. So therefore, it was one of the very interesting pieces of work from an undergraduate, Raman. He did not stop here. He continued on this problem, and he also published at least one more paper when he was an undergraduate. So you can think about it. So he's just an undergraduate student. He's already doing experiments in his college undergrad lab and publishing papers. So which also tells you that he had a very good ecosystem in which he was working and he was studying. His professors encouraged him a lot. And he also took up a lot of interest, not only in physics, but also in languages, especially in English, and also various different topics related to English literature and various different aspects of Indian literature. Now, the next phase, 1907 to 1917, is when he's now moved into Kolkata, and he's establishing himself as a financial officer, where he arrives in Calcutta in 1907 June. He also visits ISCS on the way to his work by chance, and he meets Amritlal Sarkar, who happens to be one of the important person in ISCS, who is the honorary secretary then. And in consultation with Amritlal Sarkar, he actually starts his research. They are very happy because ISCS is a place where hardly anybody would have been actually using the facility. So Amritlal Sarkar and everybody who took a lot of effort to establish that place are very happy that somebody who is really keen to do some research in that place. So as early as 1915, University of Calcutta starts assigning scholars to Raman because they see that Raman is doing very well. I'm just giving you a timeline, but I'll also talk about some of the research what he did. Ashutosh Mukherjee, one of the key players who encourages Raman, who also happens to be a senior judge in Kolkata High Court, also becomes the Vice Chancellor of Calcutta University in 1916. And he encourages Raman to join Raza Bazar Science College and kind of get himself affiliated to that. He offers a palette professorship in University of Calcutta, which is essentially a tenured job up to 60 years. And Raman also helps establishing Calcutta Physical Society, which is a discussion forum which plays a very critical role in everyday interaction. Now, during this particular time, Raman did some fantastic work on acoustics. So this is an instrument which probably some of you would be aware of and some may not. Can anybody tell me what is this instrument? Of course, people like Sunil and other probably would be easily identified, but any student would be aware of this instrument? Okay, so this instrument actually is called as Ektara. This is something which is probably prevalent in various different places across India, and it is a stringed instrument where you actually can pluck this single string and it makes a sound. There's a resonator, and there's a kind of a hollow cylinder which makes some very interesting sound. So Raman starts his kind of interest in this particular stringed instrument because he's already deeply influenced by Helmholtz phenomena, Helmholtz research articles, and also the popular lecture on musical instruments. He develops kind of deep interest in acoustics, having read Helmholtz, and he starts actually looking at the various different modes in acoustic instruments of India, especially some specific instruments like tambura and veena, where these two instruments actually have very interesting bridge architecture. So Raman studies the bridge architectures and looks at the kind of frequencies which tambura and veena can produce. And this is a fascinating kind of research where he would associate the harmonics of this particular instrument to the architecture of the bridges which are now present. Now, he doesn't stop at this particular location. He further explores the architecture of this other very well-known instrument, which is the violin. And here again, he is interested in looking at the frequencies which this particular instrument can produce, how the harmonics can be tuned. One of the aspects which really motivates him in Kolkata is that he goes on to build a mechanical violin, which is on a tabletop, where the instrument actually can be played in a very specific mechanical fashion, and you can measure frequency with extremely high accuracy. Okay, and this is an instrument built by Raman, by the way. This is very fascinating research. Now, this is just a snapshots of some of this stuff what he did, but furthermore, one of the most interesting aspects of Raman's research in the context of acoustics is the normal modes of tabla and mridangam, and these are two very popular drums in Indian music, as many of us would have come across. And what is important is that unlike some of the drums in the Western kind of a Western part of the world, the membrane at the center of this particular instrument has a density kind of deviation compared to the other parts of this particular structure. If you look at the mridangam or even tabla, the membrane actually is thicker at the center and thinner at the periphery. And this plays a very critical role because now you can get harmonics of any specific beat. And Raman went on to show and visualize this harmonics, very beautiful experiments where he uses sand patterns on mridangam to visualize the harmonics of that particular oscillation of the membrane. This is a very beautiful. These are, by the way, these are all photographs taken by Raman. So this is actually published result from Raman, and you will see beautiful kind of sand patterns depending upon where you actually tap that particular mridangam in this particular case. And accordingly, you will end up getting the modes visualized on the surface of this particular instrument. So as you can see, Raman is already building up a lot of interest in acoustics, mainly driven by the concepts of wave nature of the physical phenomena. he actually does exhaustive amount of research. That is something which you will find when you study about Raman. He is a person with tremendous amount of energy. The amount of work he has done, and he does most of the work by himself, and he also really is very enthusiastic in communicating the work what he has done. So some of the work what he's published is, for example, the acoustic knowledge of the ancient Hindus is a very beautiful article written by Raman, again talking about the Veena and even the Rudra Veena, and he connects that to some beautiful architectures in the Indian temples, and the some of the kind of percussion instruments and various different instrumentation used in such kind of architectures. So much so that he will be also invited to write an important piece in the handbook of acoustics from Germany. Again, he gets an invitation, and he writes a beautiful article which is in German and gets translated later on. Later on, Raman also worked extensively on the so-called whispering gallery effect. And this is a fascinating area of research. And probably many of you would have heard about goldsmiths in India, where if you actually whisper at one location in that particular large cathedral or some kind of a dome structure, the sound waves actually can propagate along the dome structure and reach a person who is very far away, but just around the periphery of that particular dome. And this is a phenomena which Lord Raleigh would have explored in St. Paul Cathedral. And Raman actually, when he visits England, he visits St. Paul Cathedral and repeats some of the experiments. He also goes back to also various different places. For example, Gold Gumbaz, he is the photograph. He also does some very fascinating research, and he has published some very interesting papers. If you're interested, you should actually have a look at this, look at that work. Now, let's move to the phase 3, where Raman is now a Pallet professor at Calcutta University, and also a full-time researcher at Indian Association of Cultivation of Science. So in this particular time period, unfortunately, Amrit Lal Sarkar, who is the person who gives him the job at ISCS, dies, and Raman becomes the honorary professor and secretary at ISCS after that. And his 1919 is the crucial time when he starts the work on light scattering, and this is, you'll see that it will become a very interesting direction in which Raman starts some very fascinating work. And 1921, he obtains the honorary doctorate from University of Calcutta. Mind you, Raman did not have a PhD. Okay, so MA pass was the ultimate degree he got. But he was so good that the University of Calcutta actually arranged for an honorary doctorate. And then he could also kind of take students and guide them. And there were very important aspects related to that. In 1921 is the first time Raman actually goes to England. The very first time he actually goes abroad. He visits England, as I mentioned. He also goes and does some very interesting observations and experiments in St. Paul Cathedral, and interacts with some of the people. And September 1921, where he's gone to England and he's gone to also US and Europe, and he's coming back. And now on the way back in the ship called Narkunda, SS Narkunda, that's where the real trigger question actually comes into picture. There's a bit of history where he asks, why is the sea blue? I'm going to give you the background of this question in a minute or two. He publishes this very famous paper on the color of the sea, and he writes that paper while traveling on board. Okay, this is something fascinating. He makes some observation. He always used to carries a small spectroscope and some small optical instruments even when he was traveling. And he does some measurements on board, and he ends up writing a very nice paper during that particular journey. Now let's look at the 1917 to the 1930s phase. This is the time where he publishes his very famous and very important kind of junction at which he really starts thinking deeply about diffraction, molecular diffraction of light. And I'll also refer to this essay in a minute or two. And his early students starts observing something called as feeble fluorescence, which is also a concept I'm going to introduce you And K.S. Krishnan, and who joins him as a new research associate in around 1925, is an experimentalist par excellence who does a lot of work and tests as much as 50 liquids in terms of the effect what they are observing. The crucial trigger aspect to Raman's observation comes from a very important paper written by Kramers and Heisenberg on the scattering of light by atom, where they also make a reference to Smeckel's kind of hypothesis and specific theory. And I will refer to this particular concept in a minute or two. And this actually is the connection where Raman's observation from conventional classical scattering to quantum mechanics happens. Okay, I'm going to come to that in a minute or so. And Compton receives the Nobel Prize, and this is another important piece of the puzzle which Raman connects during his scattering. And 1928, Dirac's QED is in there. So you will see beautifully everything coming into one particular row of important theories and also a very excellent experiments by Raman and the connection between them. This is where the important question is raised, where Raman writes about the sea of the blue. The trigger point to really explore molecular scattering of light is from an analogy of what Rayleigh would have hypothesis. Rayleigh, as you probably would be aware of, addressed the most fascinating question of why is the sky blue? Okay, so Rayleigh takes this particular thought process and extrapolates that to even why is the sea blue? That is a question which Raman is also interested. So in the passing, Rayleigh would have mentioned, we must bear in mind that absorption of the proper color of water cannot manifest itself unless the light traverses a sufficient depth before reaching the eye. In the ocean, the depth is, of course, adequate to develop the color. But if water is clear, there is often nothing to send the light back to the observer. Under these circumstances, the proper color cannot be seen. The much admired dark blue of the deep sea has nothing to do with the color of water, but simply the blue of the sky seen by reflection. This is the point made by Rayleigh, and Raman does not agree with that. Okay, he's actually now disagreeing with his hero, of course, in a gentle way. He mentions in his famous paper, the color, far from being impoverished by the suppression of the sky reflection, was wonderfully improved. This is his observation. It was abundantly clear from the observation that the blue color of deep sea is a distinct phenomena by itself. Okay? And this particular distinct phenomena is what he would have actually explored in terms of light scattering from the water molecules in water, in that particular sea. Now, this is where a very interesting connection happens. See, this is also a time where Raman 1921 paper is still talking in terms of the classical Newtonian dynamics kind of picture. And this is where actually he takes a kind of a very interesting, what should I say, leap of faith in terms of how to project this problem to something which is beyond the classical dynamics. And these are his words in this famous essay which he wrote. By the way, this becomes kind of a preamble to the lot of research which he does going further in next 15 years or so. So here is what Raman says. The belief in the validity of Newtonian dynamics as applied to the ultimate particles of matter has, however, received a rude shock from the success of quantum theory as applied to the theory of specific heats. Again, thanks to Einstein and Debye. And there seems no particular reason why we should necessarily clinch to Newtonian dynamics in constructing the mathematical framework of field equations, which form the kernel of Maxwell's theory. Okay, this is already kind of talking in terms of what happens to Maxwell theory in the quantum mechanical context. Rather, to be consistent, it is necessary that the field equations should be modified as to introduce the concept of quantum of action. Okay. In other words, the electric and magnetic circuits should be conceived not as continuously distributed in the field, but as discrete units, each representing a quantum of action and possessing an independent existence. Okay, this is quite remarkable. 1922. This is the time when quantum mechanics is kind of still coming into the central stage of physics, and Raman is already looking forward. And mind you, he has to understand the concept which has already been postulated. He also has to bring in his experimental kind of observations and connect them. And that is still not happened yet. Now, this is the central part of my talk and also the central part of Raman's life and the most important discovery, per se, so to speak. So these are the extracts from the diary of K.S. Krishnan. And this is happening in 1928 in the month of February. And there is a connection to that also, why we are actually now all meeting here today. And Krishnan tells, as a research student, he's keeping a research diary, and this is what he's actually writing. For the last 3 or 4 days, I have been devoting all my time to fluorescence. Okay, this is the experiment they're trying to do. The subject promises to be open out a wide field for research, since at present there is no theory of fluorescence which could explain some of the outstanding facts. Okay, there are some outstanding facts which I'm going to come to that. Recently, Professor has been working with Mr. Venkateshwaran on the fluorescence exhibited by many aromatic compounds, which is actually the molecules. The fluorescence of some liquids is found to be strongly polarized. Okay, this is the trigger point. Okay, this is the reason why a lot of questions come into picture, where the polarized signature of the fluorescent signature of the fluorescent light is what really intrigues Raman and his students. Now, this is getting more interesting. On February 7th, and this is also very fascinating, and Krishnan writes that discovered all the pure liquids show a fairly intense fluorescence in the visible region. And what is more interesting, all of them are strongly polarized. Again, keep this in your mind, it's strongly polarized. When I told Professor, which is Raman, about the results, he would not believe that all liquids can show polarized fluorescence. He was very much excited and repeated several times that it was an amazing result. Okay, he wondered how we missed this discovery all the 5 years ago. Okay, they have been really exploring this topic for a long time. Now, the interesting aspect: after meals at night, Venkateshwaran and myself were chatting together in our room when Raman suddenly came to the house about 9 p.m. at night. Think about it, and called for me. When we went down, we found that he was very excited and had come to tell me that what we had observed that morning must be Kramer-Heisenberg effect we had been looking all these days. We therefore agreed to call the effect modified scattering. This is a very important thing, going from fluorescence to the modified scattering, because of the very important kind of connection which Raman made to Kramer-Heisenberg effect. Now, all of you, especially students who have studied quantum mechanics in some detail, would be aware of this very famous formula when one comes across second order perturbation theory. One also looks at the question of what happens to photons interacting with an elementary particle like an electron, and one can actually associate a scattering cross section to that. So if you observe very carefully, you will have a summation over all the intermediate energy states, which is something which you would have also come across. And there is also very interesting factors which come into the denominator of this particular equation. This is essentially the scattering cross section associated with the interaction between a photon and an electron, and an atomic electron in this particular case. And this is the famous Kramer-Heisenberg formula. This is actually in German. If you want to have a look at it, do have a look at it. Later on, Dirac and various different people also use this formula in a very interesting way. There's also an important delta function related to this. But what is important from this particular formula is a kind of a picture what the gentlemen who are looking at these effects are building. So this is a picture which I have drawn for the sake of clarity and as kind of explanation, and slightly bit kind of made simplified. So essentially, when you have light interacting with an electron, and if you consider the electron in an atom, which is kind of bound to the two-state system, you have light which is now interacting with this electron. There is now a transition. But if the electron does not interact with this particular light in some way, such that the light which is outgoing carries the same energy, then this kind of scattering is called as Rayleigh scattering, which essentially talks about the elastic scattering process. In the so-called Stokes scattering, some amount of energy is now taken from this particular incoming light, and this particular quanta of energy is gobbled up by the electron, and the light which is now going out due to this interaction it now carries an energy which is less than the incident energy. And this scattering is called as Stokes scattering. And what is important and very consequential in this interaction is that Kramer and Heisenberg, who also refers to a very important theoretical paper in their own work, actually tell that there is also another kind of interaction which is possible, where there can be transfer of energy from the atom. In this particular case, the electron can lose energy and transfer that particular energy to the outgoing photon. Okay, and that particular scattering component is called as the anti-Stokes part of it. Okay, the conventional fluorescence generally comes in this regime, and again, without having any specific polarization signature. But what is interesting is that if these signatures are to be present in a interaction process, these signatures actually carry some kind of polarization because of the conservation of angular momentum in such kind of situations. So Raman connects this point very interestingly. And this is what happens on the day, February 28th, Tuesday. Went to association only in the afternoon. Professor was there and proceeded to examine the influence of the incident wavelength on phenomena. And he was using the usual blue-violet filter, which is a kind of an architecture they used with the uranium glass filters. And the range of wavelength transmitted by the combination being much narrower than that transmitted by the blue light filter alone. So they're using a specialized filter. On examining the track with a direct vision spectroscope, which I'm going to show you, we found that, to our great surprise, that the modified scattering was separated from the scattering corresponding to the incident light by dark region. This is the day of the discovery, and 28th February, Tuesday, 1928, is considered as the day on which Raman scattering effect was confirmed. Mind you, this was actually already going on. This was one of the most important observations because this gave a very concrete proof for what Raman and his students were hypothesizing, and the connection they were making to Kramer-Heisenberg formula. Now, the remarkable aspect of Raman is, see, if one does Raman scattering nowadays, one actually has access to very good lasers, and the phenomena what one can explore using very powerful lasers is relatively easier. So therefore, performing Raman scattering is relatively easier compared to, let's say, what they did. But Raman was an outstanding experimentalist. So he devised a very interesting technique where he could perform Raman scattering even with a laser beam. As you know, 1920s, there was no laser. So they had to actually create a kind of a monochromatic source. And what they did was they used the holy sunlight, which is abundant in India. So what they did was they used something called as heliostat, which is a brilliant idea, where you essentially have a mirror, and the light from the sun is deflected from a mirror into the lab. And this particular mirror is connected to a clock. So according to the time of the day, it actually changes its orientation such that it always sees the sunlight. It's a very smart and very neat experimental kind of trick. And you will always get maximum amount of light coming into the lab, so that you can perform the experiment as long as the sunlight is abundant and there are no clouds and other things. So the idea is, now you bring this light, you incident the light beam onto a scatterer, and you look at the scattered beam. Okay, so they are looking at the scattered beam and talking about fluorescence or scattering or modified scattering, etc., etc. So the instrumentation they use is something like this. So now the sunlight is there. Now the sunlight has various different wavelengths. They have to filter this to make this quasi-monochromatic. Okay, because if you want to look at scattering, you have to incident light which actually has large component of single wavelength, and that light is now perpendicularly projected post scattering to a direct vision spectroscope. This is what Krishnan is mentioning. So this is the initial setup for the experiments. Once you get confirmation, what they used to do is replace this direct vision spectroscope with a spectroscope. And what they do is, essentially, now you have a mercury arc in the similar case, like sunlight. You can introduce a filter, you can introduce a lens, and you have a liquid of interest, in this case, anything like carbon tetrachloride or any kind of structure, organic liquid in a spherical flask. The scattered beam is coming in, and the light is now projected to the spectroscope. You can now use silver halide films and capture photographs, etc., using this system. So this is the kind of system Raman used. It's kind of remarkable because the kind of ingenuity you need to have to perform this experiment is nothing short of amazing kind of talent. Because it's not trivial to actually do this experiment. People have tried to do such kind of experiments in the present day and age with such a kind of facility. You need to be really good experimentalist to do these things. Okay, just because it is inexpensive doesn't mean it is easy. It's quite tough in that sense. Now here is the concept. What they actually found out was that if you now take the phenomena what we have been discussing, Rayleigh scattering, fluorescence, and the so-called feeble fluorescence, the concept is that there is no frequency change for Rayleigh scattering, whereas there is some kind of polarization effect, which actually is imprinted onto the scattered light. This is one way to actually detect Rayleigh scattering, by the way. Whereas if you take fluorescence, there is no polarization effect, but there is a frequency change. What Raman and his students found is that they not only found that there was a frequency change, which was the effect why it was called as feeble fluorescence. In addition to that, they also found that it was essentially polarized. This polarization signature is what was predicted by Kramer-Heisenberg formula. Okay, that there was a very important connection, because this particular polarization signature could have happened only if you considered a quantum mechanical theory of the scattering of photons from that particular electron in an atom. So this is a kind of an architecture of scattering, as I was talking about, in a kind of a geometrical way in how you will be observing this particular effect. So there you go. Raman actually ended up kind of making this very big. So Raman, you can see this is a spectroscope which I was talking about. This is an instrument which is still preserved at Indian Association of Cultivation of Science in Kolkata. This is the first ever Raman spectra recorded, photograph, by the way. This is actually also published in his famous paper in Indian Journal of Physics, and later on also referred to in the famous Nature article. This is the most important paper, which actually ends up kind of becoming the most critical reference, which forms the foundation on which the Nobel Prize is awarded to CV Raman. He also refers to an unmodified type of scattering, which Compton would have already found out. As you probably would be aware of, if you have X-rays, and if the X-rays is relatively kind of monochromatic in nature, they're like X-rays actually scatter off a free electron. And Compton had studied the change in the wavelength of this particular X-ray because of the scattering from a free electron. And he had connected that particular principle to the quantum nature of the interaction. What Raman did was got inspired by the Compton scattering effect, and he brought that particular phenomena to from X-rays to visible frequencies. And he further called this as a modified scattering, okay, where he also observed the ordinary light, two types of scattering, as we have been talking about. One is the conventional Rayleigh scattering, the other one is Stokes and the anti-Stokes part of it. Now, this is one of the very famous spectra which Raman and his student recorded of carbon tetrachloride. There were immediately people would relate that this can become an extremely important tool, because these lines, what you are seeing, essentially becomes the fingerprint of the molecule. Okay, which means that the molecules which are now scattering that particular light have a very specific vibrational frequency, which are again quantized in nature. So therefore, they actually become signatures of the molecule and in essence, fingerprint of these particular molecules. And this has very deep implications in how it can be utilized to identify various different species. And so much so that you actually can take this kind of interaction to any environment where you do not know what is the molecule in that particular place. And therefore, you'll also find Raman spectrometer even on spacecrafts and also in missions which go to Mars and various different places. Now, this is actually the time where discovery of Raman effect, as I have described, happens. Immediately on the very next day, Raman was extremely good at making sure that his research is well known and publicized. The very next day, Associated Press of India releases the news. And on 16th March, a detailed lecture at South Indian Science Association in Bangalore, Raman gives a talk giving all the details of his experiments. And this is, mind you, the paper has already been sent out in February. So this is all the kind of further confirmations what he has done. And he is now giving details to the press at that particular time. The famous Nature paper is published on 31st March with the title A New Type of Secondary Radiation, which I just spoke about. And very important point, around 1928, the two gentlemen in Russia independently also report Raman effect, but on a solid state object. Okay, they would be looking at quartz, and in the this very famous journal, they do report about the light scattering effect. And if you look at some of the initial papers, they also call the effect as Mandelstam-Raman effect. Some of the papers you will find it. Russians actually were a little annoyed that these guys did not get the Nobel Prize, but this was actually reported much later, and there was some interesting discussion about the priority and etc. But it happened so that Landesberg and Mandelstam, in their July 1928 paper, refer to Raman's experiments. So, which means that they're really also giving credit to the Raman. And there is also very interesting explanation by the Nobel Committee later on of why they did not give it to these two gentlemen. It is again a German, Peter Pringsheim coins the term Raman effect for the first time in his one of his paper, and again it becomes quite well known across the globe. Rutherford, who is probably the most influential experimental physicist then, makes a reference in his presidential address of Royal Society during this particular time, where he mentions explicitly about this great discovery what Raman has made and talks about this. By the way, Rutherford was actually the main person who backed Raman to the hilt. Okay, you will see that even during his IASC tenure, etc., Rutherford is always the person who backs Raman. This is a very interesting connection between Rutherford and Raman. Now, the rest is history as they speak. 1930, Raman ends up getting the Nobel Prize and also is knighted, probably even just before the Nobel Prize. And it happened so that Raman booked the ticket to go to Sweden much earlier to the date of the announcement of the Nobel Prize. So it was kind of an audacity of hope in that sense, because he already preempted the fact that he probably would be getting a Nobel Prize. And it's quite amazing to see that kind of confidence, and it borders kind of almost arrogance, but it's amazing that Raman was so confident about it. Now, interestingly, Raman, although was a great researcher, he also had a lot of problems in working with people. So you would see that unfortunately across his time period, and he has a very big difference of opinion, and with some of the people at IACS. And he has to leave the place, and first of all leave as the honorary secretary. And at the same time, IAC would be scouting for its fourth director, and the committee actually contacts Rutherford asking for some suggestions, and Rutherford tells Raman is already there in India, why should you not take him? So IAC offers him the job. Okay. Before that, Raman actually is now going and receiving his Nobel Prize. He gives this beautiful Nobel lecture. This is actually from the Nobel Prize .org. You will find this very, very beautiful essay on the molecular scattering of light. And the content of this particular lecture is worthwhile to read. Just an outline I've listed here. The color of the sea, again, you see that's where the motivation comes from. The theory of fluctuation. By the way, we are in a week when we are talking about chaos. There's a beautiful connection to the theory of fluctuations. Again, no wonder Einstein also kind of gave a very important postulate in there too. And this fluctuation is connected to Einstein-Swaminski formula. And Raman was deeply kind of influenced by that. The anisotropy of the molecule, he describes the new phenomena, which actually leads to this effect, the optical analog of the Compton effect, which is also an important concept, spectroscopic characters, interpretation of effects, significance of the effects, and concluding remarks. So he actually gives a very detailed kind of lecture on these topics. Raman was deeply influenced by the pioneers of quantum mechanics also. In this case, you'll see the Raman getting his Nobel Prize, and this is Lokasundari Ammal, the wife of Raman, and Raman in the banquet, and they are also meeting some dignitaries, etc. Raman, as I mentioned, was deeply influenced by some of the pioneers. He really actually had very great admiration towards Heisenberg. As I mentioned, Kramer-Heisenberg formula played a very critical role in Raman scattering. This was with Dirac, and he was very, very kind of influenced by many of the concepts laid out by these gentlemen, and he talked very highly of these individuals. Here in one of the Lindo meetings, he's also kind of photographed with Pauli and Yukawa. And Raman, actually, you can see, was extremely well networked and also very very outgoing and very, very jovial person to interact with. That is what I learned from reading some of the stuff written by his biographers. Here you will also see Raman with his very good old friend Max Born, who later visits IISc. And here he's also with Sir Mirza Ismail. And Raman would have visited Robert Millikan oil drop experiment person. And Millikan returns the visit to India and visits Raman when he is in Bangalore. Okay. Now, 1933 to 48 is the time when Raman is a professor. He's the fourth director and the first Indian to become the director of IISc. And Max Born visits Raman because Max Born, as you know, is German and also is actually escapes Germany during the Second World War, and is now looking for a place to settle down. Max Born visits and on invitation of Raman, and he stays there in IISc for about 6 months. Indian Academy of Sciences is founded, but interestingly, Raman again falls out with a lot of people in IISc. Partly here, the problem is also because they do not like Max Born being offered a position in IISc, which Raman was very interested in. And a lot of professors who were British professors actually do not agree to Raman, and they have a lot of fight and etc. So Raman actually is then removed from the directorship, but he's retained as a professor. So he resigns. And Homi Bhabha, interestingly, also visits India during then. And 1939, he also comes to IISc. There's interesting interaction. For people who do not know, Raman also founded chemical industry with his student P. Krishnamurti, because he also felt that industries actually can help in funding and things like that. He took some initiative. In 1947, Raman also became first national professor, courtesy Government of India. And in 1948, crystal dynamics is the work he initiates. Interestingly, he actually gets into an intellectual argument with Max Born, and there is a very interesting difference of viewpoint in the crystal dynamics. In 1948, he retires from IISc. In IISc, he does one of the most pioneering works, which is very related to the acousto-optics. So in the interest of time, I'm going to keep it short and just tell you about Raman-Nath effect, where the idea is that if you now take a liquid cell, and if you propagate sound waves along this particular liquid cell, because the sound waves essentially are compression and rarefaction, they associate that to a density fluctuation due to the sound wave. Now, if your light is propagated in the direction perpendicular to this particular compression and rarefaction, this particular sound wave generator or this particular compression and rarefaction can act like a diffraction grating. So any light which is passing through this density fluctuation gets diffracted, and the diffraction pattern can be observed. Now, this is the main principle behind the so-called Raman-Nath effect. It is an extremely important effect in acousto-optics. Okay. Now, a lot of instruments which actually are used for modulation of laser signals actually are based on this particular principle. And Raman and his student Nagendranath actually hypothesized this. This is the first paper on the diffraction of light by high-frequency sound waves. This is a really pioneering work. And this is also called as Raman-Nath theory, and there are very interesting foundational concepts. There's also a very interesting Nature paper related to this effect, where Raman and Nagendranath again write about this particular principle. These are some of the foundational papers on acousto-optics, and it's still cited extensively. So, 1948, Raman is already building Raman Research Institute. Thanks to the Wadayars of Mysore, they would have given him a big grant. And Raman also, because he wants to actually go away from ISC because of a lot of difference of opinion again. And 1954 is conferred the Bharata Ratna with Rajagopalachari and Sarvapalli Radhakrishna. And in 1960s, he works extensively on flowers, color of flowers, human vision, and very interesting concepts. Raman was also very enthusiastic experimentalist. He was extremely enthusiastic in communicating science, not only to younger people, but also anybody who visits his lab. And this is something which is stayed with him for a very long period of time. He was also an excellent lecturer and speaker. You can see this is the Raman giving his famous crystal dynamics theory. You can readily see the dispersion relationship drawn here. He also is now talking about Gandhi Memorial Lecture, which is a lecture he used to give every October 2nd on the birthday of Gandhi. He admired Gandhi a lot. I should mention that. Because even during the Nobel Prize, he actually briefly mentions that he's disappointed that the great man is still in the jail. That's what is one of the things he mentions on the day of his Nobel Prize. The most important aspect in the spectacular success of Raman was actually in motivating young children. He was a big hit among children. You know, everybody who writes about Raman from that particular time period tells that he was extremely enthusiastic in interacting with children. So much so that most of the children who actually interacted with Raman have got motivated to become researchers in their future career. And there are so many people who really got motivated, and there are so many stories about this particular thing. So unfortunately, Raman had a cardiac arrest in mid-October, and Raman actually has some issue with the heart, and he doesn't want to stay in the hospital, so he asks him to be shifted to his house in the institute, and he dies on 21st November 1970, aged 82. This was the last photograph taken of Raman, probably on 2nd of October again, in 1970, after his lecture. He gave the lecture, by the way, even on that particular year. Now, just a very brief comment on Raman. Was very inspired and driven by aesthetics. He actually had huge collection of minerals. This is still present in RRI, beautiful museum, and there are all beautiful crystals which are there. You can see Raman in his attire with him holding a very big crystal, and he was very fascinated by the optics of minerals, etc., etc. Ramaseshan, who actually happens to be his nephew and also a definitive biographer of Raman, actually talks about these aspects. For example, tells you as how Raman was inspired and driven by aesthetics. These are words of Raman. The face of nature as presented to us is infinitely varied, but to those who love her, it is even beautiful and interesting. The blue of the sky, the glories of sunrise and sunset, the ever-shifting panorama of the clouds, the varied colors of forest and field, and the star-sprinkled sky at night, these and many other scenes pass before our eye on the never-ending drama of light and color which nature presents to our benefit. The man of science observes what nature offers with the eye of understanding, but her beauties are not lost on him for that reason. More truly, it can be said that understanding refines our vision and heightens our appreciation of what is striking and beautiful. This actually very much resonates one of the famous videos which you can see of Feynman, where he talks about the beauty of the flower. Okay, this is fascinating. This is fascinating to see that Raman had such deep kind of inspirations. He also was deeply influenced by great thinkers like Euclid. He really, admired Euclid a lot. In fact, this is a very famous quote. The pages of Euclid are like the opening bars in the grand opera of nature's great drama. They lift the veil and show to our vision a glimpse of the vast world of nature, natural knowledge awaiting study. So he's really, really, inspired by the everyday natural beauty and connects that to the physical phenomena. And this was typical of CV Raman. So Ramaseshan writes that Raman ended up publishing 475 papers and wrote 5 remarkable monographs, a total of 4,000 printed pages on topics so varied that one mind boggles. Okay, despite all the things other than the science he did, he was always focused on doing science. This is something which is remarkably inspiring because he could have easily stopped doing anything after he got the Nobel Prize. But, from the 1930 to 1970, 40 years, he still continued to do research. He could have easily kind of put his feet up and not do anything. It was truly affair done more with nature, mostly with sound and light, a prolonged, passionate affair lasting 65 years. Okay, that was Raman. So lastly, Rama session on CV Raman also mentions, because he also was his uncle, so he could have interacted a lot. And this beautifully summarizes what Raman was. I've never seen anyone who enjoyed science so much. The sheer joy of seeing things and doing science filled him with exuberance and excitement. He had an incredible zest for life. He enjoyed his food, his jokes, his travel, his storybooks and novels, his fights and quarrels. Okay. Yet the enjoyment he had for his science was something apart. In this pursuit, it was as if his ego disappeared completely in the presence of effulgent nature. Yes, he was truly lost in the wonder and beauty of what he was trying to comprehend. So, this is the story of CV Raman, kind of a small overview of Raman and his effect in terms of science, and also some of the history of the ideas which influenced CV Raman. Raman was also deeply patriotic, but also a scientific person. Okay, and he always felt that a society cannot go further without science. And I will end with what Raman mentioned. What India needs is science and more science. Happy Science Day. Thank you.
Thank you so much, Pavan, for a beautiful biographical sketch. It really brings the person, makes the person come alive. And yeah, you referred to many little things and incidents that we have all heard about, but I think I got a much better perspective from this. So are there any questions? Please ask, please unmute, and yeah, you're getting compliments on the chat. You can ask your question in the chat, or you can unmute and ask the question directly.
Yeah, please do. Yeah.
In one of his experimental setups, the one with the sun being focused, so I felt that in the past times, the experiments were more crude and more you'll have to put more effort into those. And nowadays we buy a lot of things from different vendors, and I feel like the previous one was better for some reason. Like, do you have any remarks on that?
Okay, I'll talk about being experimentalist and being kind of a science explorer, so to speak. See, the point is that you can still do those experiments if you want. Nobody is actually stopping you from doing these experiments. The fact that the questions what one needs to answer now actually has gone beyond what was kind of easily approachable in that particular period of time. See, an important question, and Einstein probably, I think, I don't know, it's a quote associated with Einstein that any second-rate physicist can do a first-rate work at that particular time, so to speak. Now, what I meant to say is not to demean anybody, but what I'm trying to say is that the questions, what there were, the answers to those questions could be through an experiment, which did not require so much of sophistication. But, as the questions were answered, there were new questions, and there were new depths to which one had to really go. And still we have to go. Okay, see, for example, LHC in CERN, that's actually one of the biggest experimental physics setup you can ever imagine. Now, you cannot actually address the question of Higgs boson or determine the presence of it without such an outstanding effort of not only the instruments, but also the people. So the thought level which is required to go to address that question is very, very high. Similarly, if you want to do Bose-Einstein condensate experiment, the amount of effort you need to take to cool down that gas of atom to an extremely low temperature is not a mean task. Bose-Einstein hypothesis, the postulate was already there. Okay. But the 1998 was the time when they got the Nobel Prize. You can think about it. It took us such a long time to really come up with an experimental setup to realize that. And by the way, I should mention, whenever I talk about Bose-Einstein conductions, there is also an important aspect related to laser cooling, laser trapping, optical tweezer, which is something I'm very fascinated about. And the foundations had to be laid one step at a time. And finally, it culminated to something more sophisticated. So to answer your question, Sagar, it doesn't mean that you cannot do simple experiments. There are possibilities to even do simple experiments, but that is actually driven by the question you are asking. If you want to really go a little deeper and find out, for example, what is the structure of, let's say, a nucleus, so to speak, you had to go to a technique which really probe the time scales and the spatial kind of extents of that kind of an object. So therefore, the technique what you use and the experimental setup what you use is driven by the question what you are trying to address. So which means that I would say that horses for courses. Okay, you can still do some very beautiful experiments in fluid dynamics, for example, at a scale and at a cost which doesn't require a lot of expense. But you will be addressing a question which is slightly different, for example, compared to, let's say, something in particle physics or somewhere. So all are important. All are important. This is very, very important because physics is so vast, so diverse, and also so beautiful. That is which makes the whole of physics so interesting. In my opinion, I would say I would be interested in doing all kinds of things. If I want to do some kind of an experiment, nobody will stop you from doing it. People have been doing it. You should not think that nobody is doing very simple experiments like that. But you will have to then do more analysis. You'll have to also back it up with some very strong, interesting theory, which is accurate and also which has models, computational approaches to these problems. Everything is possible in some way or the other. But I would say it is still possible to do such experiments if you want to do it. But that is motivated by the question what you are asking. That is what I want to say.
Thanks, Pavan. We'll go on, but I'll quote one comment in the chat. So Srihari has written, depends on the scales we are probing, doesn't it?
Yes, absolutely right. Absolutely right. See, I tell you something. To just give you a reference for some of the questions, what people are interested in, optical microscope. All of you would be aware of 2014 Nobel Prize in chemistry actually went to something called a super resolution microscope. Okay. Until that particular discovery which happened, again, which dates back to roughly around late 1980s to early 1990s. And that is the time when people started thinking of how to break the diffraction barrier of light. Okay, until then, the probability of you detecting a single molecule on the surface of a cell was very low because you did not have the resolution to do that. So as Srihari mentions, the question what you're asking also depends on the scale at which you are probing the problem. So you will have to then go further and do an experiment. For example, if you want to do single molecule experiments, you will have to use techniques which actually will be able to probe those single molecules with high accuracy. And therefore, you will have to use different kind of sophistication to probe the problem. But don't think that bigger the scale, easier the problem is. It's not the case because there are also many complicated problems. For example, weather, right? It is probably, you all know that the Nobel Prize in Physics actually partly went to the model systems, which actually predicts the weather. So scale doesn't always just correlate with the sophistication of the thought and effort required to solve that particular problem. But it is an important point. It's an important point. I would surely. We can do simple pendulum and watch, but with higher accuracy, it gets very sophisticated very fast. True. See, for example, stroboscopic experiments where people actually capture something at a very fast rate. Okay, you probably would be aware of the fact that stroboscope experiments dates back to almost 100 years, where a horse which was moving, a galloping horse which is moving, was captured, and for the very first time they could see that at a particular instant the horse was not in contact with the with the floor. The horse literally actually floats at a small instant. You cannot visualize that. you know what? That particular analogy is the analogy what Ahmed Zivel uses to talk about the femtochemistry, where he's talking about the molecules actually are vibrating at a rate which is much faster than the vibrations of the light or the pulse rate at which the laser beam can come. So therefore, you actually have to have your shutter of the camera, in that particular case, the laser beam, kind of going off and on at a rate faster than the image which has actually been captured, okay, or the object which has been captured. So time scales, spatial scales, all these actually play a very, very, very important role. And as Srihari mentioned, that plays a very, very significant kind of, it has a significant bearing on the phenomena, what has been discussed here.
If I can add a couple of comments, Pavan,
Yeah.
you mentioned that thing about second-rate physicists doing first-rate work. Actually, I think that's due not to Einstein, but Dirac.
Dirac, is it? Yeah.
Because I have heard, actually, I have attended a summer school where Dirac was present, and he actually mentioned
Wow.
that in those so-called glorious days of physics, he said it was glorious days for physicists because even a mediocre person, I'm quoting his exact words, even a mediocre person could hope to make a profound discovery. This is not a comment about Raman, by the way, but there were a lot of people from those days. There were a lot of open problems because, imagine nobody knew why the sea is blue. By now in 2022, people will have asked all the obvious questions million times over. So it becomes more difficult.
But I think Einstein also refers to Newton happy childhood days or something like that. That is a statement by where he's talking about. I think Einstein writes the foreword for Newton's Optics. I have that book, and Einstein writes that particular. You're right. Actually, that's the Dirac is the one who actually talks about this. But it's fascinating, that really it's worth going and revisiting the history of physics.
Yeah.
I probably, at least personally, it gives me a great joy. It gives me a reason to study whatever I'm studying, know people behind it. And one point I should mention that you would observe all the times and all the places where I would be discussing Raman's students were all men. Okay, this is also a signature of the time in which he worked, and also there is also a lot of information which has only recent times that there was an issue of inclusivity at that particular institution where he conducted research. This is something to keep in mind and be a little bit more open. But I would not hold it against Raman right away. But the research and the science is fascinating. So that's the only focus of this particular interaction. And therefore, I've kept it that way. Yeah.
Just to put it in context, even Princeton University was not happy to admit Jews until the 1940s. So, and practically, I mean, that is the one community that has contributed maybe maximum to their great distinction. So, in those days, discrimination was.
But that's actually not the story now. I think the whole of Princeton.
Yeah, absolutely.
From Witten to everybody.
Yeah, everybody. I mean, that's, Jewish culture has a very strong this thing. Anyway, that's not the point. The point is that discrimination in, a century ago was a completely different level, which I think it's difficult to comprehend now.
Absolutely.
I would request, since there will be an informal session going on afterwards this, if everyone agrees, right? But for now, I would request everyone to switch on their cams so that we can have a nice group photo of the event, since one of the sad parts about this is that all of this has to be on camera. So yeah, please, I'll request all the participants if they can turn on their and give our professors a chance to see all the students as well, actually.
Yeah, great to see. I hope to see everybody on campus at some point.
Yeah, in a few weeks.
Yeah.
I hope so. I think everyone will be in-person classes by the end of March, probably.
Yeah, that will be great.
Yeah. Dheria Bhandari makes a very important comment. I would simply like to comment, Raman and Chandrasekhar seem to share a passion of doing very interesting work on board a ship. Absolutely right. Absolutely right. Again, I've written a blog. In fact, I can share it later on also about Raman and his nephews. Okay, there were stalwarts. Many of them, Chandrasekhar is a story by himself. In fact, on a personal kind of angle, I have slightly higher admiration for Chandrasekhar even compared to the Raman, but for whatever reason, I really deeply admire Chandrasekhar that way. Outstanding, they're all people who were very dedicated to science and also had their own way of working and thinking. That's fascinating.
Pavan, can you put in the chat window the URL of your blog?
Oh yeah, sure. I would right away do that. In fact, that's a good thing you mentioned about. In fact, I'll of course